Hello, everyone. So, this is the second in our very unusual two-part series here on Spacetime. Our great quest to understand the universe, to find the mechanics of base reality, and to understand why our universe exists at all, seem to be at an impasse for the past century after the great revolutions of relativity and quantum mechanics. So, together with Professor Brian Keating, astrophysicist and friend, we're joining forces to bring together some of the leading researchers in particle physics and in cosmology to look for a way forward. Brian, great to have you on Spacetime again.
It's wonderful to be back with you and all of our esteemed guests. It's a real treat and thrill for me.
Last time we had an amazing lineup. We had Max Tegmark, we had James Beecham and Stefan Alexander, and I think we really, started to converge on some useful thoughts. I really encourage you to go back and watch that. It's only 90 minutes long, as will be today's. But today our luminaries are no less luminous. And I'm just going to give you a few words on each of the people we have here today. My pleasure is to introduce Eric Weinstein, who is a very unique case, holding a PhD in mathematical physics from Harvard, but did not pursue the traditional academic route at all. He's an author, a mathematician, an economist, and managing director of Teal Capital. And Eric practices physics outside the academic establishment, and in that regard is most famous for his geometric unity proposal. And you can go to his podcast, The Portal, and to the Portal Wiki for the details on this radical new idea, and the links to that will be in the description. Sabina Hossenfelder is a theoretical physicist at the Frankfurt Institute of Advanced Studies, where she works extremely broadly, but generally in quantum gravity research. Sabina is also a prolific writer for popular media, a blogger, and a YouTuber. Sabina, I really want to thank you for your incredible YouTube channel. These wonderful physics videos, really, I've learned more on your videos than certainly anywhere else on YouTube and possibly most of the internet. Welcome. Finally, Lee Smolin joins us. Lee has been a central figure in our quest for the deepest laws of the universe for decades and has worked in many and perhaps all of the ideas that we will discuss today, from loop quantum gravity, of which he is one of the founders, to string theory, to the foundations of quantum mechanics and the philosophy of physics. And Lee is a founding member of the Perimeter Institute and is the author of many books, actually, including, quite appropriate to today, The Trouble with Physics, The Rise of String Theory, The Fall of Science, and What Comes Next. Also, Time Reborn, From the Crisis in Physics to the Future of the Universe, which I have a very dog-eared copy right here. It's my favorite beach reading. And more recently, Einstein's Unfinished Revolution, The Search for What Lies Beyond the Quantum. Lee, it's an honor to have you on board.
It's a pleasure to be here. Thank you very much.
I was wondering, Lee, would you be able to just give us a quick overview of what we mean by when we talk about a quest for a theory of everything?
Yes. Well, it means the theory of everything means different things to different of us, and we should make that clear. To many people, it means a unified theory of the elementary particles and their interactions. And that's a hope which has been ongoing for a long time. And there has been, as we'll discuss, some interesting ideas, but very little progress. Another thing you might mean by a theory of everything is a unification of the theory of gravity with quantum theory and with quantum field theory and the rest of the elementary particles. And that's the aspect of the problem that I've mostly worked on. The question of how to fit together our understanding of gravity, space and time, and cosmology, probably given to us by general relativity, with quantum physics. There's a third thing you might mean by a theory of everything, which is the completion of quantum theory, because there are a number of people who are of the view that quantum theory is incomplete and that the issues needed to complete quantum theory are the reasons for the slow progress in the other ways of going at a quote theory of everything. And my own personal view, which I suspect will not be agreed to by my friends here, is that the fundamental troubles are having to do with foundations of quantum mechanics, with the notion of space, of locality, and that the overall set of problems stemming from cosmology, the initial conditions of why this universe, why these elementary particles and their forces have ultimately to do also with issues that would be needed to understand how quantum mechanics really makes sense. And the last thing I'll say is that I think everybody's asking the wrong question. I think people who are still wondering at why the elementary particles and forces have the structures that they do, the particular symmetries, the particular arrangements of particles, are like biologists before Darwin trying to understand the a priori reasons why there are snails and cats and dogs without the key idea, and the key idea is evolution. And I think that the question we should be asking is how do the laws evolve, under what dynamics, and why did the universe choose the laws that we have, this particular mix of elementary particles and their forces? And that the progress will come to focusing on the mechanisms by which laws evolve rather than the particular properties of the laws. So that's my provocation to my friends here.
We feel provoked. That's fascinating. Yes, it's also echoes a little bit of I think where we got to the end of the last session, and Max Tegmark echoed similar views about looking to this hole in the foundations of quantum theory. But before we get into those details, perhaps Sabina, would you mind giving us a similar state of the field address?
Okay. Yeah, so as Lee already said, different people mean different things by theory of everything, some of which I think are better motivated as a target of our investigations and others not as well motivated. As James said the last time, we have this issue that the standard model of particle physics doesn't want to cooperate with gravity. So we're in this peculiar situation where we have two theories that each individually work perfectly fine, but if you try to use them together on the same situation, then it just doesn't work. And it's not like these situations just do not exist in the universe. They do very well exist, for example, in the very early universe towards the Big Bang or in the center of black holes, but also in principle, every time we bring a particle into a superposition of two locations, then we don't know what happens with the gravitational field. And that's because we have not been able to combine properly quantum theory with gravity. So that's just an inconsistency, and that's something that the theory of everything should be able to do, just to tell us what happens in these circumstances. But then other people want the theory of everything to do more. For example, they wanted to explain why the particles in the standard model have this particular structure. Why do they come in three generations? Why are the gauge groups these particular gauge groups? And it would also be nice if these gauge groups would not just be sitting next to each other, like we have these three different types of symmetries in the standard model, but if they were combined to one larger symmetry. And this is normally called grand unification or a grand unified theory. And so a theory of everything, for many people, especially for string theorists, should combine both this grand unification with quantum gravity. And so it's no secret what I personally think of this necessity that we have to remove the inconsistency between quantum theory and gravity is a real one. So we know that this just cannot be how nature works, right? Nature doesn't have any inconsistency. There has to be an answer to that question: what happens with the gravitational field of a particle in a superposition? But when it comes to the structure of the particles in the standard model, then that's maybe you may say, well, that's not pretty the way that it is. And I would say, well, who cares what you think is pretty? The standard model works just perfectly fine. So to me, banging on this question, I'm very sympathetic to what Lee said. Banging on this question, like why do the particles fall into this particular pattern, is just not particularly constructive. It's not something that will move us forward. I can say a little more about approaches to quantum gravity if someone's interested in that.
Well, I would say we're all very much interested in that, and actually, this is a good idea. Just starting out, still setting our stage. Let's do perhaps a quick survey. I don't know if you want to take some of those, Sabina, and maybe Lee can take some.
Yeah, it won't take long. So one of the approaches to quantum gravity is loop quantum gravity, and I think I'll let Lee say something about this. Then I already mentioned string theory. This is probably the best known approach to quantum gravity, which in principle also contains a grand unification. So the idea of string theory is that everything is made of strings. So that it sounds pretty lame, but it turns out that if you try to formulate it mathematically, it's a highly restrictive framework, and out comes an interaction that looks like gravity. So string theory, when quantized, gives you a theory of gravity. And when people realized this in the late 70s, early 80s, everyone was very excited about it because it looked like they had stumbled upon the theory of everything. And then there are several other approaches to quantum gravity in particular, which focus on resolving this inconsistency between quantum theory and gravity. For example, there's causal dynamical triangulation. There's basically an attempt to discretize space and then take a continuum limit. That's based on a path integral approach, this idea of Feynman. There is an idea which is called asymptotically safe gravity, that originally goes back to an idea by Steven Weinberg, which says that actually we can quantize gravity the same way that we quantize the other interactions. And it's just that if we do it naively and don't think about what the result is, then it looks like that theory is sick. But if you look at it a little more closely and think about it, then the theory is actually fine. It's asymptotically safe. And so the interesting thing about asymptotically safe gravity is that, well, for one, to my knowledge, it's the only approach that correctly predicted the value of the Higgs mass. And I think that's an underappreciated success of this idea. But it also, in principle, contains, or it's able to contain a grand unified theory. So asymptotically safe gravity is a contender for a theory of everything. It's somewhat of a mystery to me why it doesn't get more attention. And then maybe finally let me add emergent gravity, because this came up in the discussion last week. This is the approach that, among other people, is being pursued by Eric Weinstein. So the idea of emergent gravity is to say that the attempt of taking general relativity and trying to quantize it to get a theory of gravity is as ill-conceived as the idea of taking, say, water and quantizing it to get a theory of atoms. It just it doesn't get you what you want, namely a more fundamental theory. So in this idea, gravity is really an emergent force that comes from the interaction of many, many tiny constituents, which are sometimes called the atoms of space-time. But you shouldn't take this phrase too seriously. In any case, the idea is that gravity comes from this interaction of many microscopic constituents. And the big question is, what are these microscopic constituents? Is Eric still there? Why don't you let Eric say something?
Eric, please, if you don't mind.
Well, so this is the embarrassing part, because I'm not a physicist. I'm also not cowed by where we are in physics. I have a somewhat different impression, which is that we haven't really seen theories of everything. And so we haven't thought enough about what the really difficult conceptual problems are. And I've analogized it to Escher's drawing hands. How do you create a background in the form of a piece of paper? And when the paper generates ink, and the ink generates pictures of hands which draw each other, like you're bootstrapping reality into existence. So there are conceptual problems with theories of everything that we've been avoiding, in the same way that if you're going on a Jabberwock hunt and you've never met a Jabberwock, you have no idea what it is. You're bravely going off with your shovel and your BB gun and your compass, but you have no idea what it is that you're actually trying to track. And I think that where we are is very interesting and exciting, which is that up until 50 years ago, we were going great guns, and then everything suddenly came to a halt. We just didn't think a lot about the way in which we had an old project called unified field theory. And then somehow it got changed to quantum gravity, that if we could only quantize gravity, that would be the holy grail. And I think that was an amazing piece of sleight of hand, because these were different views. Unified field theory is much closer to what we've been describing as grand unified theories, which take 3 out of 4 forces. And of course, we name it some bizarre thing like grand unification because it's less grand than actual unification, just to confuse people. But in large measure, we've had unifications. Maxwell's unification of all of electromagnetic phenomena is probably the greatest one. What's happened in the last 50 years is that we've had a complete stall out in terms of the ability of theoretical physics to predict what comes next, tell us what to do to find really new stuff. And as a non-physicist, I can tell you that from outside, it looks like the political economy of physics is destroying the actual research potential of the field. So that's what's fascinating to me. And I'm really looking forward to doing as much battle as our internet connections will allow with Sabina, my friend and colleague, because I think she's a great curmudgeon who refuses to get swept up in the nonsense. And I do think that there is a case to be made for looking at the nonsense around string theory, around quantum gravity, and the sleight of hand by which we had one set of dreams replaced by another. And somehow, bizarrely, nobody noticed that the unified field theory concept melted away, and it became the imperative to quantize gravity, not only to possibly reverse it. And the idea is maybe we should geometrize the quantum because gravity's always been geometric. That's really what the big story of the last 50 years has been, is the geometrization of the quantum. But because the propaganda in physics is so oppressive, we don't even get to tell what we actually did do, and we're stuck with the story pretending that we did something with it, which we didn't do, which was quantum gravity. And what we did do was geometrize the quantum, which is both with something called geometric quantization, principally in the 70s, and also geometric and topological and conformal quantum field theories, that's the big story of now. We failed in physics, but we super succeeded at figuring out why the edifice of quantum field theory is a coherent whole rather than a grab bag of techniques that somehow just barely managed to work.
Sabina, maybe you could respond directly. I think this is what a lot of people came for. So
I think Eric is right that in the foundations of physics there has been too much attention on very few isolated problems that in the end didn't lead us anywhere. There have been too many people all banging the same drum. And now the problem is that they are refusing to accept that it didn't go anywhere. And what we could really need is a larger diversity of approaches. For example, like Eric's maybe, which in all honesty, I don't understand a great deal about, but we could certainly need some fresh input there. My issue is that I think physicists have not paid enough attention to the question exactly what has gone wrong. It's like all these ideas that they have tried with grand unification and string theory and supersymmetry and some other things, and attempts to quantize general relativity that in the end didn't go anywhere. They haven't really looked at just why these approaches failed. So I think there's some self-reflection that is missing in this community.
When you say that these approaches have failed, and perhaps I'm thinking of string theory in particular, string theory predicts this vast mathematical structure that may or may not describe what the universe is, but where it's failed is to produce testable predictions. But does that mean it's wrong? Or does it just mean we've run out of humanly accessible space for those testable predictions, and we're at the point where we are exploring the untestable?
I think we should be bolder, and we should say that the string theory program has failed, right? And the way that we should say that is they told us what they were going to do, and they told us what the time frame that they were going to do it in would be, and those things didn't happen. Now, you can always add epicycles effectively, and they've added a tremendous number of epicycles. So the issue of whether anything is salvageable is completely different.
Eric, when you say they, who are you referring to?
So the problem crops up is that you had a prehistory of string theory before 1984, maybe where it was used for strong interactions. Then it has a resurgence in 1984 with the anomaly cancellation. And at that point, something really dangerous happens within the physics community, which is that the physics community piles into string theory with the other things that we've tried not working particularly well. And so there's a claim, which is that everybody believed, and it's not true. There were tons of critics, including people like Feynman and Glashow in 1984. String theory was always playing by its own rules. It told us what it was going to do. It told us about how long it would take for it to do it. It said that there were only a finite number of theories to investigate. This is before they kept changing things. Simply put, string theory and the string theorists told us after 1984 what they would do. And then they kept changing what it was that they were saying, right? So that it went from being string theory, where it was only about strings because they had reasons why higher dimensional objects didn't exist, to brain theory. It went from a finite number of theories to a continuum with those as its extreme points. As the field learned more about what it was saying, it kept changing what it said it was going to do. So we've had multiple iterations as string theory figures out that it hasn't been capable of making the strong declarative statements that it's made at every juncture. So the issue is that there is the corpus of string theory, that is what has been mathematically learned, and they've found mathematical structures. But to claim that those mathematical structures are the structures of the world is a statement where I would have to say the community has failed because it told us what it was going to do, and then it repeatedly failed to do what it said it was going to do. That isn't to say that they might not pivot and find something new to do, and I welcome that. But yes, it has failed multiple times.
Eric, can I just address that? Because in experimental physics, it's not uncommon to have rather extreme budget overruns. I don't know anything about this, but I hear that from experimentalists and building ambitious projects that you're always optimistic in the beginning. So I think treating it as if it's a contract or a pledge or a swear, I think that's, not fair to what the ultimate goal is. The goal is to accomplish a certain product delivery, not to do it, explicitly in a given time frame. I think that's standard.
Let's agree. The issue is that the community said, we are the only ones with the ball. We have the ball. All eyes on us. We will do this. Everyone else doesn't count. And so my point is, no, that's not how science works. You guys made a call, which is that you were the sole standard bearers for physics, and you were wrong. And you need to pay that price before we continue the conversation. With respect to
Lee has his hand up.
Yes, I would put it the following way, quoting Dick Feynman. This is from a conversation with him in the late 70s. He said, if there's a question and lots of smart people have tried to answer a question and failed, then maybe it's smart to think that they're asking the wrong question and to try to ask a different question. My sense is that, and I don't know if my friends here will agree, is that almost nobody is working on the questions that were driving those of us in the early 80s and late 70s to get involved in things like grand unification and string theory, which is to understand if there's a structure to the elementary particles that can be comprehended. There are a few people, Eric is one of them. There's Cole Furry, who has some very interesting ideas having to do with octonians. There's a handful of other people. And the situation is not very hospitable. If you, Cole and some other people who work on these ideas about octonionic structures have a hard time getting on the archive, which is embarrassing. And meanwhile, there's a vibrant community doing some interesting things, but I'm just repeating myself, there is almost nobody working on the original problems that motivated people to seek grand unification or unification of particle physics and gravity.
And Sabina, you recently in your video where you kind of call out these new theories of everything, which are in the zeitgeist, as you might say, and the question of why are these new theories like Wolfram's, like Eric's, like Garrett Leacy's, like Holmes, why are they proliferating? And you make a statement in the video and in the Nautilus piece based on it. You say that the whole idea of a theory of everything is based on an unscientific premise. Some people would like the laws of nature to be pretty in a very specific way. And I want to do a Gedanken experiment, as you might say, if you permit my crappy German, and just take us back, to 1959, and then ask, were people guided to seek electroweak unification, prior to its creation? They weren't saying, here's something that would be beautiful if we could find it. Let's throw everything into the stew pot and see what comes out. And then if it looks pretty, then we will accept it. I've never done science like that. I'm not a theorist, but I doubt that theorists do that. It's more that in retrospect, something might appear beautiful, but I don't think that's ever the flight plan. We never set off and say, I want to go all the way to the North Pole, so let me start by going, to 89.9 degrees, because I know it's very close and very symmetric. So anyway, it's a long question, but is that the way that you think theorists are actually operating, that we're using beauty as a flight plan, as a roadmap?
I think that's how the methodology in the community has developed, yes. And I'm not just saying that because that's my personal opinion, but because I talk to people about this. This is what my book is all about. I've literally been traveling around and asked people, what they think about beauty as a guide to the development of theories and the foundations of physics. And it's become very, very clear that they pay a lot of attention to it. And you don't have to look far, on the internet to find example of this, where people go on about how string theory can't possibly be wrong because it's so pretty, or the same thing with supersymmetry, and so on and so forth. And I just think that's an unscientific argument, and I think it's terribly embarrassing if scientists go on and make claims like this. Now, as I said earlier, one has to be careful when one talks about these approaches to a theory of everything. There are two different sets of questions here. The one is a good question, which is how do we resolve the inconsistency between quantum theory and gravity? That's a hard problem. It's a well-defined problem. There has to be a solution to that. Now, as Lee said, that was one of the starting points that got people excited about string theory. But nowadays, there are few people who are actually even still working on even solving that problem. What most of them do is they deal with the theory in anti-de Sitter space. And for all we know, our universe is not an anti-de Sitter space. And if you ask them, why do you deal with anti-de Sitter space? And don't think about how to actually quantize gravity in our universe. They're like, because we know how to deal with anti-de Sitter space. So it's like the stereotypical example of the person who's looking for the keys under the lamppost, because that's how they know to solve the equations.
That's what the dark
The other part of the question is the one that I think is not a good scientific question, which is how do we make the standard model prettier by combining these symmetry groups and so on. I just don't think that question will ever lead us anywhere. But let me say something else about this example that you mentioned with the electroweak unification. The problem with the theory before the electroweak unification was also a problem of inconsistency, because without this unification, the theory is not renormalizable. It's basically the same problem that we have these days with the quantization of gravity. And so this was a good problem which required a solution, and people found the solution, and it led to a huge amount of progress. So maybe I can add that actually the problem is quite similar in the sense that they, in both cases, the theory was non-renormalizable, but the solution that people used for the electroweak interaction was to realize that since it's a short-range interaction, you can solve the problem by introducing a massive gauge boson. So this solution does not work for gravity, because we know just observationally that the gauge particle, if you want to call it that, for gravity is to good precision massless. So it's kind of a similar problem, but the same solution will not also work for gravity.
So Eric and Lee, you both have quite provocative perspectives on the scientific method as a whole. Eric, I want to start with you, and then I want to go to Lee. So Eric, in the context of the scientific method, one thing that frustrated many of our listeners last time was that we were basically saying things about, apple pie and hot dogs or whatever you want to eat. Everybody can agree on, yes, we need more experiments. Maybe we don't agree on how much those experiments should cost. But I do think that, there's kind of a lot of blandishments that, it would be great to have more data coming in. But that kind of does feed into this notion that there is this Popperian sense of what constitutes doing actual science. And if it's true that we can't falsify something presently or in our estimation, maybe ever, that is not worth pursuing. And I wonder, what's your take, Eric, on how overarching we have become as physicists with Karl Popper and this dictum of falsifiability?
Well, this is a very difficult problem, in part because you had a very bad recent history with one subset of the community totally abusing ideas like beauty. And so Sabine is, in fact, correct about the abuse of beauty as a cover story for why you're not shipping product. But she's, in fact, incorrect about beauty at a far deeper level, which is where she and I hopefully can find room to disagree, which is this is an extremely dangerous part of the real scientific method. The real scientific method is everything that has ever worked to get us reliable knowledge, not just the fairy tale that we tell people that if they brush their teeth and remember to floss, that they'll be invited to Stockholm. And this idea that we should come up with a hypothetico-deductive method, we should come up with ideas, then we should challenge them in the laboratory, and we should retool. Life's a lot weirder than that. And the key problem with beauty is that it's a little bit like the Blackbird, the fastest airplane ever. Almost nobody could fly it. Same thing with beauty. Almost nobody can get any water out of that well. But the tiny number of people who were able to get water out of that well, I would say the three most important people in my estimation of the 20th century would be Einstein, Dirac, and Yang, even over Weinberg. Those are the people whose equations that we all use, and they're all on record as talking about beauty as a guide. And so you have this problem that it's an extremely elitist and therefore a very unpopular thing to say, which is, no, the Blackbird is an amazing plane. There are only three guys who can fly it. Well, beauty is absolutely an amazing way to do physics, and there have only been a tiny number of people who've been able to get it to work. Yeah. So the modal person, Sabina's absolutely right. That person is probably lying about their prospects for success. That person is probably going to crash and burn. So let us agree that in the hands of the modal physicist, beauty is a terrible guide. That is not the argument for beauty.
We're all supermodal. There's no average physicist, right? So Sabina has her hand up, and then I want to get to Lee. But Sabine, you had a quick response.
Let him finish. Let him finish.
She's giving me enough rope to hang myself, as you could tell. With respect to what the real scientific method is this, to be blunt about it, renormalization theories of scale have been incredibly enervating, because the physicists have an idea of here's the gauntlet that any theory will have to run at the end. And the people who know that gauntlet find very different things beautiful, because it's anything that is a candidate. In general, too many of us outside of that quantum field theory community don't appreciate the dangers and difficulties and the pitfalls that are besetting us on all sides. Unfortunately, that community also is incredibly enervated from guessing, which is the reason that nobody works on reality anymore, for the most part. It has to do with the fact that nobody has an idea of how to function in a straitjacket quite this tight. And I'll be happy to hear what other people have to say.
So you look at Sabina, you look in your article recently in Nautilus magazine, do we need a theory of everything? And you say, what do I think about Lee's and Weinstein's and Wolfram's attempts at a theory? Well, if scientific history teaches anything, their method of guessing some pretty piece of math and hoping it's useful for something is extremely unpromising. Sabina, aren't you accusing Eric of the very thing that he's saying is problematic?
Well, Eric's only one person, so basically he can't, as one person,
and he's 10
problem
sigma.
as a community.
He is 10 sigma over the mode, right?
Let me maybe comment directly on what Eric was just saying, because it's something that I constantly get to hear, usually from physicists and not from mathematicians. But it's this argument: look at these great people like Einstein, Dirac, Weinberg, who've been talking about beauty. It worked for them. Okay, so why is that a bad argument? Because it's cherry picking data. Okay, so you also have to take into account all the people who've been talking about beauty for whom it did not work. And there are lots of examples of this in the history. If you look at people like Heisenberg, Eddington, or even earlier, this whole story with vortex theory and the Platonic solids and so on. So you have all these people in the history of science who've been going on and on about beauty. And maybe you would say, from today's perspective, these ideas were not all that beautiful, but that's because you have this hindsight insight that where the ideas didn't work. The point is that at the time when they were making their conjectures, their sense of beauty was not working. And you can also just see this, basically happening right now. People have been using this very specific notions of beauty for the development of theories of everything, grand unification, and so on. And they did not work, and they continue to not work. So maybe I should clarify, though, that my problem is not generally with using arguments from beauty, because I'm very much with fire. With firearm, whatever works. Okay, so if beauty works for you, that's fine with me. The problem with these arguments from beauty is that you have so many people all using the same very narrow ideas of beauty that have become pretty much dogmatic in the community. And then people do not get the message, the feedback from nature that these particular notions of beauty are just not working.
Is that truly? Because in your book, again, it's a classic book, The Trouble with Physics, 2006. You talk about all these dead theories that were beautiful, and you even hint that maybe supersymmetry won't be the saving grace. But can you?
I never thought supersymmetry was that beautiful. I think it's one thing at the nature of advice that scientists tell each other. And it's another thing to try to make a working principle and make a doctrine of it. So I agree partly with either of you. I mean, at my PhD defense, Stephen Weinberg afterwards pulled me aside, and in very appropriate for that moment tone, he said, "Can I give you some advice?" And I said, sure. And he said, I'm going to pass on to you the same advice that my PhD advisor gave me at my PhD. And I said, sure. And he said, that advice is every once in a while, think a little bit about the weak interactions. And then he smiled and he said, that really worked for me. And I think that scientists do pass down advice like that. And one of the pieces of advice is look for something which is beautiful. So a few times, just speaking personally, a few times in my life, I've come upon something, a calculation or an idea or a framework, and had the emotional experience of, wow, that's really beautiful, which came along with, that's really new. I've
Mm-hmm.
never seen that before. And it has a wonderful coherence, the way that the parts fit together. And I think that that's part of the experience of doing the science. But I never put in a paper,
Mm-hmm.
doubly special relativity is true because it's especially beautiful the way the parts fit together. And in fact, Sabina was the person who demolished the theory, not on the basis of it not being beautiful, but it not having a good local structure that we expect theories to have in quantum field theory. And so I think it's a matter of what you take it. There is this experience, a personal experience of coherence and simplicity, and those are good things. But I don't think they should be properties that you hold up in an argument about whether something is true or whether there's evidence for it.
Yeah.
I think this is a fantastic point. Actually, one of our YouTube commenters, I think, sort of summarized this, Draria 8, clarifying that beauty in physics is symmetry plus simplicity. I think it actually would behoove us to maybe define what we mean by beauty, but I think certainly there's a sense that really beauty is, rather than a rule, it's a razor, the razor of beauty, in the same family as Occam's razor, and this is based on a real observation that complex systems like our universe tend to emerge from simple laws. It's true essentially all the way up, and it just turns out that mathematical elegance often means fewer moving parts within your mechanics for the universe. So is not that a useful guiding principle?
I mean, I think that's right. I think that what the problem is, we say the word beauty as it's shorthand for something, and it has to do with an economy. So Richard Dawkins said that the power of a theory is what it explains divided by what it assumes. And so beautiful theories tend to assume almost nothing and give you almost everything. And so effectively, a theory of everything more or less has to be beautiful, because it is the idea that you're going to have a self-bootstrapping of all of the Baroque complexity that we see in our world of 3 generations, 16 particles in a generation, various interactions at various strengths. To try to imagine that this comes from a source, it makes more sense that this will hang together. And this is also, we know, post, let's say, investigations of the 1980s in geometric quantum field theory, is that we understand now that quantum field theory would have been discovered by mathematicians studying Bordism theories if there were no particles at all. It is a well-defined geometric topological framework, if you will. And as a result, we know that effectively things are held together much better if they are geometrically motivated, just in the way Lee was talking before about background independence. Once you learn to think in a particular way, you don't have to continually check to see that you're not coming up with nonsense like pseudo-tensors and the like. But let me just give a warning. We, aside from the technical difficulties, we're going to spend almost the entire time talking about things that don't work, things that have been thoroughly explored, whether it's loop quantum gravity or string theory or grand unification. And the most important thing, if you really want to talk about this as an active subject as opposed to a sort of historical subject, is that you have to say, okay, well, why is it that we can't escape the gravitational pull of the past failures? Why are we still talking about all of these same things that we know not to bear fruit, that have been thoroughly investigated? This is Sabina's point about their idiosyncratic programs versus large programs. The large programs have the benefit of having been explored by large numbers of competent people. And so we more thoroughly know that nothing is likely to come out, no offense to Lee, of string theory, loop quantum gravity, because we've actually explored them a fair amount to know that they don't yield up the sort of fruits that people were expecting, whether it's the Ashtekar variables or in the case of loop quantum gravity, or the anomaly cancellation in the case of string theory. But what's fascinating is that we're not actually interested in processing our own failures and then saying, And now what?
Well, I wonder sometimes if we could cut up in that fallacy of the appeal to popular opinion. That's not the way that science works, nor does the fallacy of authority work either.
My provocative quote is that the scientific method is the radio edit of great science.
But Lee, you've even gone further and said things such as maybe there isn't a scientific method. Can you elaborate? I know you only have a few minutes, but it's very precious, and I'd like to understand this provocative statement from you about the scientific method and whether or not...
Let me say something very specific, which is a pointer. Most of my thinking about the scientific method is framed by Paul Feyerabend that Sabina mentioned, and Feyerabend's against method. But I've tried to go, I think he has correctly characterized many of the issues, but I don't, and he's raised the question, how is it that science works if there's not a method in the old-fashioned positivist way? But he didn't answer that problem. And I don't know if it succeeded or not, but the contribution that I've made to try to answer that problem is chapter 17 of The Trouble with Physics. And let me just refer people to that. It's an approach which is not completely original with me. The main idea of the approach is that science has to be explained as the product of a community. And there are ethical principles which guide how the community functions, always imperfectly, and always recognizing that there's cheaters and people pushing the boundaries in the community. And I try to characterize what it is about this community that leads from time to time to consensus after there's been disagreement in terms of arguing from the evidence. So, and the kind of theme of that philosophy or that description of what science is, it starts by saying that human beings are fallible and we easily fool each other and we easily fool ourselves. And science and the scientific community is a collective set of functions and tools which, when used properly, are good at finding error. And I think, Brian, you'll agree, you're an experimental cosmologist, and probably 99.9% of what you do is seek to find errors and eliminate them.
That's right.
And that's what we theorists do when we're doing our job as well.
Yeah, and Sabina, I don't think you would disagree. You talk about this as in your advice that you gave in an interview that we did, advice to a young physicist, to look for the inconsistencies, to use that as a guide. I wonder, for someone who is not known for effervescent optimism and sanguinity on the state of physics, you do write recently that, you say something to the effect that there's no need for quantum gravity to explain any current observation, but hopefully, and this word hopefully struck me in your language, hopefully this will change in the coming decades. On what basis do you have to hope for such a thing to happen?
Well, so there's a long-standing myth that is very common in the physics community that you cannot possibly test quantum gravity ever in our lifetime, not in the next million years and so on, because, and I believe this briefly came up last week, you need to build this collider that's the size of the Milky Way, and it's not going to happen because we have to face economic reality. And there are lots of variants on that idea that you need to have an unrealistically big machine to ever test quantum gravity. May that be this big collider, or you have to build a graviton detector the size of the planet Jupiter and put it in orbit around a neutron star, stuff like this. So you can make a lot of fun estimates on that account. But this fails to neglect that a particular specific property of gravity is that the interaction becomes stronger with larger masses. So strictly speaking, when we say that we can't test quantum gravity, What we're actually saying is either the masses are so large that we can measure the gravitational field, but then they don't have quantum properties, or we have objects that have pronounced quantum properties, but then they are so light that we can't measure the gravitational field. So that's the problem that we have. Another thing is that there has been a lot of technological progress in bringing heavier and heavier objects into quantum superpositions, which offers the possibility that at some point you may just be able to measure the gravitational field, and then we can figure out what's with the quantum properties of gravity. And there's still several orders of magnitude that people have to bridge in the experimental community, but we're not talking about 40 orders of magnitude. We're talking about something like 5 to 6 orders of magnitude, and that's in an area where there is a huge amount of progress.
Well, Lee, if you do have to head out, perhaps you can maybe say something at the end of the last session. I asked everyone to give their impression of really what is the end game going to look like. You know, what is it that we need to find a better question, or do we have any hope of actually asking these fundamentally philosophical questions about
No,
existence?
I think I said at the beginning what I think the question is, which is what is the dynamical mechanism by which laws evolve? And that's much more important than that is the explanation for what the laws are. And it's not a beautiful symmetry. It must be a beautiful mechanism, something analogous to natural selection. And the other thing which I personally think is likely is that a common resolution of the problems in quantum gravity and quantum foundations will involve the idea of locality. And what will happen to the idea of locality is that space will turn out to be an emergent structure. And therefore, fundamentally, what's local and what's not local is dynamically determined and emergent. And that will be the source of the resolution. That's my bet. And I'm happy to work in the scientific community where I have the privilege, and I have to say it is a privilege, to work on these questions. And I agree very strongly with Sabina and Eric, who in different ways are pointing to the problem of the diversity of people and ideas in the field, especially of physics.
Thank you so much for your insights and your profound parting words. Also, this is stuff that we all need to think a lot more about.
Thank you. This has been
Thank you, Lee.
Yeah,
Thank you.
Bye.
With Sabina and Eric can address those questions as well. I can't resist because the people in the comment section are wondering, Sabina, about your perspective, and Eric, your perspective. This is not a rumble. They're not here to defend themselves.
Wait a minute. I was told that this would be a rumble. Otherwise, it would
I said, let's get ready. TOE rumble. But we're not going to rumble. Sabine would kick your butt anyway. But the point is, what do you guys think about what's in the air? Why are there so many new theories of everything? Eric, why do you think, what inspired, your theory dates back to 2013 perhaps, but Stephen Wolfram's, Garrett
my dates back to 1983 or something like that.
No. What do you make of Wolfram's theory, and what do you make of this critique that I get from Sabina sometimes? Basically, I don't have time because we all have limited time, but I know enough not to feel like it's worth devoting a lot of attention to these. That being said, you did go to Hawaii to meet with Garrett, Sabina. So, first, Eric, what's your take? Be charitable because he's not here, but on the approach of Wolfram, or would you take it seriously, and if not, why not?
Well, first of all, I take every independent researcher trying a theory of everything who's trying not to fool him or herself. I'm supportive of that because there's almost nobody who fits that description, unfortunately. As to why this is happening, again, I'm just a little bit concerned that we have this thing called theories of everything. We're not really talking about theories of everything as the first opportunity. Let's be more honest than we'd like to be. In general, because mommy and daddy have failed, the kids are misbehaving. So the idea Stephen Wolfram was just talking to me, and he said, I really thought I was going to run into all the same resistance that I had before. I didn't realize that the community wasn't in a position to offer it anymore. So having effectively lied and failed to say what it was doing and where we were and how things were progressing, there's a huge credibility gap with all the people who are supposed to be tamping this down. So we have to be honest that in general, my guess is that Lisa would have been the one person in this community who would still be, viewed at some level by the core community as kind of on board with the core. Sabina is, of course, a rebel, talking as she has about string theory. Lee and his trouble with physics, same thing. The core community is not able to suppress this stuff as much as it used to because it is not, in fact, credible. And that is a large reason for why it's possible to roam around and to, say things on the internet. Now, I'm in a very interesting situation where I have almost 500,000 views on the YouTube for geometric unity on that lecture. And yet there really hasn't been a substantive discussion of what's in it, what it's about, or anything. I mean, we just always talk around physics now. And so I think it's really important to recognize that we don't actually do physics much. What we do is, if somebody told you that there was an attack by a joint Russian-Chinese force on Western science, right? Science in Western Europe, the Americas, and Japan, let's say, and that it was going to work by getting everyone to talk about Popper, everyone to talk about string theory, about the scientific method, about Feyerabend, we can't even pronounce his name or spell it. All of these things is we talk around what it is that we're supposed to be doing. We don't actually do it. We don't talk about muons. And it's fascinating to me that we're talking about theories of everything or as if it's like some sort of, like there are none that have been accepted. And the issue of who is claiming one, Stephen Wolfram isn't claiming to have a theory of everything. Garrett Lisi is not claiming to have a theory of everything. These are people who have some sort of a program, and we have an idea of why. Wolfram believes that his rules generate complexity that wasn't present, obviously, in the rule. So particularly generative rules in the computer science cellular automata perspective are incredibly generative. So his claim is, it looks like these could generate differential geometry and therefore the underpinnings of the standard model in GR. In Garrett's case, he had an original hope, which is, okay, there's 16 particles in a generation. It has to do with spinor groups. There are weird ways in which spinors and what would be called the adjoint representation can be fit together in what are known as exceptional Lie groups. I bet the largest one contains a threefold symmetry called triality, which gives you the 3 generations of matter. Now that didn't work. And it didn't work for reasons I told Garrett at a conference organized by Sabina at Perimeter, where Lee is, bringing it all back together. And that didn't work. Now, Garrett is sort of onto something else, but he won't exactly admit that the old program didn't work, even though, he based it on triality of E8, which is a non-trivial observation since it's not manifest. So, those are noble attempts to do something, but they're not theories of everything. And we're not honest or clear. I think that there would be a breakout of theories of everything if anyone had one, but it's almost impossible to fool yourself into thinking you have one because the constraints are too great. And, it happens to be that maybe because I'm not a physicist, I can fool myself into thinking I have one. But I just don't believe that theories of everything have broken out. What has happened is that people have become bold because Qumran and Ed and David aren't going to shut everyone down. And if you know who those names correspond to, then you know exactly why it was that a lot of dissent was suppressed.
And Sabina, do you have a rubric? Do you have a checklist, that you say a theory has to pass before I will use my time to investigate it further?
Well, first, maybe let me make a comment about what Eric just said. You complained that there has not been any substantive discussion about geometric unity. I think that's because no one has any idea what you're talking about in the first place. I think you're severely underestimating the communication problem, and you have to work much, much harder on that. And yeah, I watched your lecture, and I think that I'm among the 500,000 people who watched your video. I'm probably one of those who have a pretty good starting point in understanding what you're even talking about, and even I only have a very vague idea what you're even up to. And so let me then come to your question about why we're seeing this renaissance of theories of everything. I think that's partly what we're seeing is people coming of age who've grown up with this idea that there has to be a theory of everything. It's just a sociological aspect. People who went into physics in the 80s, maybe late 70s, early 80s, something like this, they were all told there has to be the theory of everything, and it's the next logical step after the development of the standard model. And before you know, we'll have found it. It's just that it didn't happen. And so then we've seen like 20, 30 years, people going on about how great string theory is, and that in the end didn't pan out. Okay, and now you have these people who've been silently working on their theory of everything, in secret on their desk, and nobody wanted to listen to them because everyone's been talking about string theory, who probably now are encouraged to finally give it the final push out. And I suspect that we will probably see some more of that. And I think that's a good development, even though, as I said, I'm not terribly excited about people trying to solve non-problems. Nevertheless, you never know what they will stumble upon.
Yeah,
Personally, if I can finish this, I'm almost done. What I find more exciting is that we're seeing much more interest now in the foundations of quantum mechanics, which has, there's not a lot that has happened for half a century or something, and it's now, again, it's mostly driven by technological development, that there are more things that people can test, and now there's this revival of interest in the foundations of quantum mechanics, and this has come up a few times in the discussion here. I think that the solution to the question of what do you do about quantum gravity will ultimately come from a better understanding of quantization and locality in quantum mechanics.
So I definitely want to give Eric a chance to respond, but it sounds like, to paraphrase, Max Planck, it might be
I think
wait for a few more funerals for physics to progress. Matt, you were going to say something, but I think we should give Eric a chance to respond to that body blow landed in the 9th round by Sabina.
Yeah, and not just a chance to respond, but also maybe a chance to tell the audience when we might see more about geometric unity. When should we be monitoring the?
All right. So first of all, Sabina, I thought you were going to say something like this. This is preposterous. By the way, I think the world of Sabina, her integrity and her curmudgeonly nature have been a huge boon to physics. So keep doing what you're doing, and there's no one I'd rather fight with. Given that, the gloves are off. Sabina, that's not true. Look, assume that you had a space-time manifold, right? And normally we need a four dimensions for that. Before you have a metric, here's a one-dimensional manifold in the form of a circle, okay? Now, it happens that you have to create in geometric unity an ambient space, which would be a fiber bundle, okay? That would look like, in the case of a circle, a disconnected object, which we will call Y, call the hair tie X, which is that band around the core. And this is Y, which is the space of metrics. These would be time-like, these would be space-like metrics, right? So the idea is that an Einsteinian space-time is a wrapping, if you will, of a hair tie around the core. And the idea is that the physics is taking place both on the hair tie and on the core, all right? And so if the space-time metric is down here, you're going to pull back different information at the bottom of this core than if it were at the top. That's just saying it's a section of the bundle of metrics. That's straight up Einstein, right? What I am saying is that the bundle of metrics, this object Y, has a funny feature, which is that it has a metric on it almost. So I'm going to put a toothpick right now through the core of the roll, representing what I would call the horizontal tangent space, which is not pointed along the tube. If it was pointed along the tube, then the Y structure would have a metric, and then it could have things like electrons and muons and neutrinos and the like. But in fact, it points off. So one of the issues of geometric unity is pushing this horizontal subspace along the tube to be a perpendicular to the vertical subspace. Therefore, the space of metrics that Einstein gave us actually weirdly almost inherits a metric without any choices of a metric on the original space. On that, you define all of your particles, and the 10 dimensions that Einstein gives us of the coupled partial differential equations are the same 10 as the spin 10 unified theory. Okay? So the idea is you have a coincidence. You learned about something involving 10 in the case of Einstein's general relativity. You also have 10 cropping up in grand unified theory. 10 is 2 times 5 for the SU5 theory. If you think about something called the Petit Salam theory, that's usually given as SU4 cross SU2 cross SU2, it should be called spin 6 cross spin 4. 6 plus 4 is 10. 10 is coming up over and over and over again. It's also d squared plus d divided by 2 if d equals 4, right? All of these things give you a structure where there is no internal symmetry groups. And that was the huge problem with supersymmetry, is that you never got rid of the double origin story. You had a space-time origin story, and then you had a fiber origin story where out of the blue, or in Yiddish, inmitten drinnen, coming from nowhere, you put SU3 cross SU2 cross U1, which, because you never pulled that out of anything organic and geometric, the idea is that when you did supersymmetry on top of it, by the way, which is not a symmetry, I don't know why we insist on calling it that, you were working on the wrong group. The idea is that where you saw the Lorentz group is where you should use the gauge group. Now, Sabina, what you call the gauge group is actually technically called the structure group. So I'm not talking about the finite dimensional objects that you were talking about before. But you should form the infinite dimensional gauge group. And just as you form the inhomogeneous extension of the Lorentz group, to form the Poincare group, you should form the inhomogeneous extension of the gauge group, which is an infinite dimensional gadget. Do supersymmetry on that, remove the internal symmetries, and generate them by the virtue of the fact that the proto-spacetime, before it inhabits the province of Riemannian or semi-Riemannian geometry, you should look at the bundle of metrics, realize that that almost has a metric on it, therefore it effectively almost has spinors on it. And closing out this little riff on geometric unity, one of the problems that people keep talking about, oh, we can't quantize gravity. You have a bigger problem than that, which is that the electron and the quarks and the neutrinos and all these particles that are matter depend on a particular choice of a metric. They don't exist in the absence of one. So you have, in the case of a photon, you have the C in which the photon is a wave, if you will, and then you have the wave itself. And you can say, well, I don't know where the wave is between observation. If you don't know where the metric is, then you don't know where the ocean is between observations. And the difference between being at the beach and not being exactly sure where the waves are versus being at the beach and not being sure where the Pacific Ocean is an entirely different world of pain. And for whatever reason, the physicists are not particularly bothered by this. So one of the things that geometric unity does is it takes the issue of the fact that the electron bundle, the medium in which the electron is a wave, doesn't exist between observations of the metric. And it says, we're going to solve that for you by working over the space of all metrics, showing that that has an almost metric coming from the fact that it has a chimeric bundle, which is partially along the space and partially pointing away from the space. Geometric unity tamps that down. And that means that electrons are defined between observations of a gravitational metric, which could be up here or down here, because the entire space of metrics effectively has a metric. So I don't believe...
Let's give Sabine a chance to respond. All right. Yeah, let's take 1 more minute. All right.
Sabina, you said this thing about like this doesn't solve problems of physics. Bullshit. I mean, you don't know why there are 3 generations. I'm telling you that there are 2 generations plus an imposter generation. You don't know why the world is chiral. I'm claiming it isn't chiral. I'm claiming that it has 2 chiral halves that decoupled with an illusion of emergent chirality rather than fundamental chirality. There are all sorts of things that I'm trying to show you. I'm trying to show you the fact that there are 2 Lagrangians, not one, and that the Dirac equation and the Einstein equations belong to the first order Lagrangian, and that the Yang-Mills Lagrangian equations, and the Higgs or Klein-Gordon with potential belong to the second order Lagrangian. So I don't think that it's the case that this has nothing to contribute. You may be very busy, but I don't think that that is the problem of geometric unity. I could certainly explain this to you, in terms that are familiar manifold theory.
Sabina.
So I kind of have the impression we're talking a little bit past each other, because you just said, let's just pick this. You're telling me why there are 3 generations, and that supposedly solves the problem. But I don't see that there is any problem with just having 3 generations. That's the whole point that I've tried to get across. There's nothing inconsistent with the standard model the way that it is. There's no problem to solve. It's the same thing with chirality. So the standard model is chiral. What's the problem with that? The one problem that we really have is the missing quantization of gravity. And so on that count, I would say, well, if you claim that you have successfully quantized gravity, then please tell me what's the gravitational field of that electron in a superposition. Can you do the calculation? Can you show that your theory is UV finite? Which, by the way, string theorists still haven't shown, at least not in our actual universe. So that's still an unsolved open problem. And also, I regret to say, but if you don't understand what people find hard to grasp about your ideas, maybe you should get a little bit more feedback about just exactly why it's incomprehensible.
Well, in the case of, so you just said something that's slightly incomprehensible to me, which is, for example, let's take your chirality point. What makes the decision about left versus right-handedness? I mean, in other words, if the universe has a beauty mark, in the sense that, let's say, Marilyn Monroe or Cindy Crawford had a famous beauty mark, what chose the asymmetry to break left or to the right, positive or negative? That's not a problem.
No, that's not a problem. Why is that a problem? We have a theory that works. That's fine with me. I'm afraid I'm an instrumentalist.
I see.
But surely this is then about getting to the fundamental question: what is our theory supposed to do? Is it merely supposed to describe the universe, or is it supposed to be deeply explanatory of some of these philosophical questions about
Get on a T-shirt.
Why is the universe?
I just think that fundamentally that's a question which is not in the realm of science. The best thing that we can do is we can say, well, we have a lot of observations. What's the most economical theory that we can write down for this? And this has also come up a few times in this discussion last week by Max, I think Techmark, who brought it up, and Eric also already said this. A good theory is one that explains a lot from a little. And so we can certainly push to that a little harder, and we can always push a little harder. But in the end, as Einstein said, you can only make things as simple as possible and not any simpler. And maybe the way that the standard model is just as simple as possible. And the only thing that's missing is
Sabina, how do you reconcile that with your well-known stated position opposition to things like the future circular collider that our guest last week, James Beecham, spoke so highly of, where it's almost like it's not really a choice between doing the FCC and doing climate modeling. It's really the FCC, and at least in my particle physics friends are telling me, or nothing. And it's the future of particle physics. And aren't you cutting off potentially this goal based on the fact that you're saying, two different things. You're saying, on one hand, we have to get more data, and we can use the data to refine the models. But what if you cut off? Let me ask you this question. It's simpler. If you were, the queen of the planet, more so than now, but if you were and you had infinite resources, where would you be putting those resources? Tell me theoretically. Postdocs, experiments, where would you put the infinite amount of resources? Forget about the other ways we could use the opportunity cost outlay.
I would put my limited resources in an educational program that teaches all physicists that resources are not unlimited. Because we have to make decisions about where to put our money. And the message that I have to try to get across is that putting a lot of money into a big collider is not a good investment. There are better experiments that we could do for less money that have a larger expected payoff. It's just currently not a good way to invest our money.
And Eric,
And I have to say, maybe let me add this, that physicists, and I've been part of this community for a long time, have basically made it a taboo to even ask the question, how expensive is it? Is it worth it? They'll stand up and say, oh, let's not talk about the money. And I'm like, well, what planet do you live on? The planet that I live on, money matters.
Sabine, it's not really true that, we do spend a lot of money on education, and I don't even mean, to this, I know you're kind of being tongue in cheek, but what about the postdocs? I've had people say, Eric, we have too many postdocs. The field can't afford it. I personally don't have enough as an experimentalist. It's hard to find. But where would you spend resources, part B and part A? Anything that you wanted to respond to that you haven't had a chance to do yet?
Well, sure. The first thing is I'm not a physicist. Let me be very clear about that. Second of all, I have a very difficult time with the physics community. Third of all, you guys need vastly more money. And as much as I'm disappointed in you, and as much as I'm pissed off and angry about the way in which the community has fallen into a state of what I would consider to be disrepair, the key thing is that there's something painful about watching the community that birthed the World Wide Web, the devices that we use to communicate with each other, both through the semiconductors and through electromagnetic spectrum, all of the wonders of theoretical physics more or less powered the entire world. And in terms of the economy, what ended wars, what have you. It is obscene that the theoretical physics community and its experimental allies have to ask for billions of dollars like a beggar with a bowl in hand when you actually provided the universe with most of what we take for granted as powering the modern world. And you guys signed the world's worst licensing arrangement ever. So the first thing I would do is to put money into renegotiating your deal with the universe, because these are not taxpayer dollars, they are physics dollars that we allow the taxpayers to make use of in large measure. You can reframe this. And the fact that you guys are actually not talking about pushing out the budget constraint is obscene. We saw this in public health, where people were talking about how should we spend the pittance that has been given for tropical disease. And the economists in the US had a brilliant idea, which is, why are we talking about a pittance? Let's push the budget constraint way the hell out. So the first thing is that where we are is pathetic. We should give you guys a collider, even though it's unlikely to work. And we should stop carping about a few $1 billion. It's pathetic, it's preposterous, it's ridiculous. So I think that that's the first frame of mind, which is I refuse to work in a pauper's framework, given our military spending. You guys are SEAL Team 6 for the human mind. We should keep our physicists fat, happy, and fighting with each other rather than mathematicians online. I appreciate that. And what I would say in terms of what Sabine is saying is, look, I don't think that this stuff is all that confusing. I think that, in fact, the key idea is that we're not that jazzed about theories of everything. We want to talk around theories of everything. We want to talk to sociology. We want to talk to economics. We want to talk to history. We talk everything other than actually saying, hey, does anybody have any new ideas? And this is really funny because, in effect, there's no reason for proceeding funeral by funeral. It's preposterous. Everybody's out of ideas. If you were a prominent person and you had major ideas, we'd know. And the key issue is, why are we not doing something that is more vital? And the answer is that at some level, Sabine is playing a very important role. The curmudgeon, the skeptic, the person who, says, show me. I think that that's really important. I think that there's a cautionary tale, which we don't understand well enough, involving Rosalind Franklin and Watson and Crick and Chargaff. And the idea is that both Watson and Crick were irresponsible. They just were. They were irresponsible as scientists. And Chargaff, who thought that they knew nothing about biochemistry, and Rosalind Franklin, who thought that they didn't have enough reason to think it should be a helix, that they were just copying Linus Pauling's alpha helix from protein. All of these people got it wrong, and the irresponsible people got it right. And the issue of encouraging more people to be somewhat irresponsible and hopefully pay back whatever they've stolen from the intellectual till by the end of the day is far better than this thing, like what Lee was saying before about good science. I'm so bored of oatmeal. I don't want to eat my fiber anymore. I don't want more asparagus. At some point, you just want to have a big slice of like warm apple pie with ice cream.
Eric, we're going to have to wrap up. These are inspiring fighting words. But before we close, I do want to get one last piece of inspiration from both of you, besides thinking more about the weak nuclear force. What advice would you give to a young aspiring physicist? Sabina?
Well, I've already said this, right? I think that it's very exciting that there is a renewed interest in the foundations of quantum mechanics. And I think basically that the future is there. So, look at that.
What about you, Eric?
I would say look at the fact that nobody asked the question about why 10 in spin 10 grand unified theory. I would say if the universe had new particles, how do you know that these are 3 generations if you don't know that they wouldn't unify with those new particles differently if you up the energy scale? I would say to you, why is it that everybody talks about complaints about locality? Nobody talks about the Tia-Patoti-Singer index theorem with its non-local eta term that crops up out of nowhere. I would say that people don't investigate the issue of what supersymmetry actually is if it is not a symmetry. Why is it that we accept 2 origin stories just the way you would in the Old Testament with Lilith and Breshit? You have one for the substrate that is the Einstein space-time manifold and another for the SU3 cross SU2 cross U1 internal and auxiliary symmetry groups. Make sure that you have one origin story before you start trying to apply supersymmetry. I would say any one of a huge number of things, but the key overarching thing is that the field has misexplained itself through the same leaders repeating and reciting the exact same things over and over again. Go back to a period before 1984. Look at a book called Shelter Island 2, when just before string theory's anomaly cancellation happened, and look at Murray Gell-Mann's opening remarks. If you have to come up with an understanding of what the field was before the madness took over, look at geometric quantization, look at geometric quantum field theory, and understand that we have 2 different geometries, one built on Charles Ehresmann's theory, one built on Bernard Riemann's, underlying the 2 halves. Stop talking about this in the same terms that Ed Witten and David Gross taught you to speak about all of these things, and instead find a new way of formulating, because there are millions and most people are acting as if they're Stepford wives, repeating the same thing. Stop worrying about money, get somebody to raise funds for you.
And speaking of raising funds, we'd be remiss if we didn't mention Sabina's wonderful book, Lost in Math, which is available in paperback and hardcover. Eric, you have the Portal Wiki and also the Portal Podcast. Matt, do you have any concluding remarks?
My concluding remark would be to look at Brian's excellent book, Losing the Nobel Prize, and you should also definitely head to his podcast, Into the Impossible, where you'll actually hear conversations with these 2 geniuses and plenty of other people. It's extremely enlightening.
Sabina, absolute pleasure. And Brian and Matt, thank you guys for having us.
Thank you all. Thanks for this rather unusual episode of a mildly chaotic space-time.